Hello and welcome to our bonus episode of Lecture 16. That is part 6. In this bonus episode, we will address an important question left over from the previous time, namely, what happens to free precession when the precessing body is not axisymmetric? So, namely, what happens when I1 is not equal to I2? So, in this case, it turns out that we can solve the same set of equations when we don't assume that I1 is equal to I2. And we can write down what the precession frequency is. It starts out similar enough. It's equal to omega 3, 0, the unperturbed initial frequency. And then that's where the differences come in. Here we will have I3 minus I1 divided by I1. And here we'll have I3 minus I2 divided by I2. So you can see if we set I1 equal to I2, then this will reduce to delta I over I. But in the case when I1 is not equal to I2, we're getting this answer. Plus, notice that the last equation over there, it is actually telling us that omega 3, 0 is not going to be an exact constant of motion in this case. Why is that? Well, it's because the system is no longer axisymmetric. So that's why it's not going to be conserved. But if we assume that the perturbations are small, then omega 3, 0 is conserved not too badly. And so we can use this as an approximate solution where omega 3 will be roughly a constant. What you can immediately see from here is that in certain cases, omega squared doesn't have to be positive, which means that there is no solution for free precession. That actually means that the rotation about that axis, about the third axis, actually is not going to be stable. And so when does the stable solution with omega squared that's positive, and therefore with omega real, actually exist? That happens when either both of these terms are positive or whether both of these terms are negative. And therefore, what we can say is that if I3 is biggest or smallest, then the solution will be stable. However, if I3 is in the middle between I1 and I2, then one of these will be positive and the other one will be negative, resulting in a negative omega squared, which means that a real solution doesn't exist, which means that the rotation around the third axis will not be stable. Great. With this, we can try and test this in practice. So let us actually take a brick. So this is one of the boxes that delivered a card reader, which I'm using to transfer this lecture from the camera. And what we're going to try and do and figure out which one of the three principal axes of this box is going to be unstable. So this is how the box looks like. So that is the box, and this is how it looks like in 3D. And now let's draw its axis. So this will be its z-axis. This will be the x-axis. And this will be the y-axis. Actually, I think that I need to flip the axis, right? And so in this case, the quiz will ask you which one of the three axes, x, y, and z, actually is going to be unstable. Which one has the value of I that is in the middle between the two other i's, and therefore which axis suffers from the middle axis instability. So what we're going to do afterwards in lecture 7, we're actually going to throw this thing up in the air and test it out. And you can do too. Find a packaging box, or if you're brave, play around with your cell phone, but I wouldn't recommend to do that. And see what happens when you spin it up around each of the three principal axes. So one of the axes will be like that. That's the x-axis. The other one will be y-axis. And the third one will be the z-axis. So with that, I'm going to leave you here to ponder this question, and I'm going to see you in the last bonus part of lecture 16. Have fun. I'm going to see you on the other side. Hi, welcome to the last part of full bonus lecture 16. Part 7. Wow, that's a lot of parts, but you know, they're fun. So what is it that we're going to find when we run the experiment? I hope you already have done yours and you found the answer. So let's try a bunch of different axes. So let's try and draw this one again. And remember that this one is the z-axis. This one is x and that one is y. So which one of the three principal axes will have the largest and which one will have the smallest moment of inertia? Well, let's look at the y-axis first. Well, see, everything is very compact. Almost all of the mass is as close to the y-axis as possible. So y will be less than both of the other ones. So what is the largest one? Well, let's see which axis has the mass distribution around it that is furthest away from the axis. And what are the two others, z and x? Well, you see that things are closer to z because they are at most this plus a little bit. We can neglect this transverse thickness. But for the x, the furthest away is the diagonal, which is definitely longer than that distance. So Ix will be the largest moment of inertia, and therefore Iz will be the middle one. So it means that we expect rotation around the z-axis to be unstable. So let's try and check this out. All right, so let's first take a look at how stable rotation looks like. So stable will be either x or y. So it will be either around that axis or around this axis. So let's try and see what happens around the y-axis. 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay, so kind of rotation is maintained. So what about the x-axis? Let's try and see what happens when I spin it this way. Woo. Yeah. Okay, so it looks like it's pretty stable as well. What about the z-axis? So it will be this way, right? Oh wow, did you see that? So when we spin it up like this, the rotation starts to become chaotic. Let's try it again. Yeah, did you see that? So let's compare it to this. Or let's compare it to that. See the difference? So indeed, we have experimentally confirmed that rotation around this z-axis is unstable. Wow! So that's a lot of fun. So I hope that you found something similar in your experiments, and I'm going to see you now for real in lecture 17.1, which I will post in the next couple of days. So have more fun with your home supplies during this pandemic time. Bye-bye.